Hey guys, welcome to this set of videos on advanced portfolio optimization. Today we're going to compute optimal weights based on a 1-year rolling window period of data to estimate the means, betas, covariance matrices, and diagonal matrices of the residual variances for our one-factor model. Our sample period is going to start in 1992 and we're going to work our way through 2018. This re-optimizing weights and portfolios on an annual basis is best done in 2 separate steps. So first we're going to create a for loop to calculate the optimal annual weights, and then we're going to loop again around those weights to calculate the portfolio returns. So the first thing we need to do is create a year index to roll our variable I around. So we're going to assign the variable year, and then we're going to use the floor function, which is part of the rounding family. And this is essentially just rounding the integer down to the next whole value. And then we're subsetting on the first column in our returns matrix, and we're dividing by 10,000 just to get the year. And now if we populate that in the console, we can see that each daily observation has its own year that can be looped around. And then we're going to assign a vector of 1s, and we're going to assign that variable IVEC. Video will be calculating 2 portfolios: the global minimum variance portfolio and the global MVP with an index model-based covariance matrix. And you'll see that in a second. So our next step is to create a matrix of 0 that has a number of columns equal to the number of industries and the number of rows equal to the years in our sample. We're going to assign this a variable of WG1 for our global minimum variance portfolio. And our second portfolio is also an MVP, so we can assign that a variable WG2. We'll start with the for loop here and assign the variable I to be iterated from 1992 to 2017. Now the body of our loop is going to start with the 47 industry returns. And again, we're subsetting this based on the ith iteration of the year, which in this case will start at 1992. And then we're just subsetting the columns from 2 to the 48th column, or denoted as the number of industries plus 1. Now for our index model, we want to define the returns again, subsetting the row based on the ith iteration of the year, which is 1992. And our factor is going to be the total market return, which is denoted from the 49th column. Next, 2 premature calculations need to be made for implementing our momentum strategy later. And essentially, we need to take the average return of the 47 industries as well as the standard deviation. And these calculations are going to come in later. And then finally, to calculate our minimum variance portfolio, we need to calculate the covariance matrix. And we're going to assign a variable Z sigmat. And then the last thing we need to do to find an analytical solution is invert that covariance matrix. And we're going to assign a variable V inverse. And then we're going to use the solve function to do that. Completed our intermediate calculations and can now implement the optimal weight formula. If you're unfamiliar, I would just review the must-know and MVP optimization in my PowerPoint. So our numerator is just going to be the inverted covariance matrices multiplied by a vector of 1s. And then to populate the optimal weights based on the ith year, we need to iterate the rows of the optimal weight vector. So it's going to be I minus 1991, which will essentially be 1992 minus 1991. So the first optimal weights are going to fill in within the first row, and then the second iteration will be the second row, and so on. Notice that we've built the optimal weights within the body of the loop. And this formula right here is pretty much just saying that the optimal weights are proportional to the inverse of the covariance matrix based on the ith year. The 2 unknowns we've been estimating so far have been the mean vector of returns and our covariance matrix. Any error in estimation of those 2 parameters can greatly skew our optimization process. So now we're going to take a different approach and use the index model to calculate the covariance matrix with more precision. We need to calculate the variance of our factor from the index model. This is later going to be used to calculate the covariance matrix, but notice how we're not using the 47 industries, but rather the total market return. Next thing we need to do is we need to run a regression of the factor on our 47 industry returns, and this is going to allow us to generate our betas. Now we want to store those betas in a variable, so we're going to call that Z betas. And then from that regression we just ran, we want to extract the coefficients, but we need to subset it to the second row, so we're generating the betas and not the intercept. To calculate the idiosyncratic risk of the assets, we now need to extract the residuals from the regression we just ran. And this is done the exact same way you extract a beta, except this time it's just $sign residuals. The next thing we need to do is insert those residuals into a diagonal matrix. So we're going to assign a variable DMAT, and then we're going to use the diagonal function. And then within that, we're going to use the ls.diagnostics function. And within the regression we just ran, we're going to populate the standard deviation of the residuals. And then we're going to square that to get the residual variance. Now, to calculate our covariance matrix, it's going to be broken up into idiosyncratic risk and systematic risk. The DMAT variable is going to be our idiosyncratic risk, and that's going to be added to our systematic risk, which is our factor variance multiplied by our respective betas. Our covariance matrix is now estimated with more precision because some of the noise has been taken out via the idiosyncratic risk calculation. And the last thing we need to do is invert that covariance matrix. Finally, I've gone ahead and calculated the optimal weights of the MVP based on a single index model. The calculation is exactly the same as we did earlier in this video, so there's no sense in repeating it. This is the end of the video as we successfully re-optimize weights annually, but in our next video, we'll work to loop those weights over our return vectors to better examine how effective rebalancing is.